Okay, let's unpack this. Look, if you're learning endocrinology, whether you're a third-year medical student or just, trying to get your head around this massive field for your career, you know how quickly it all just piles up?
Oh, it's a mountain of information. It really is.
Right. So our mission today is to do a really targeted, high-yield deep dive. We're using a fantastic medical review source as our guide, and we're just going to pull out the absolute essentials, the stuff you really need to know.
And we should probably begin at the absolute core principle. I mean, forget all the hormone names for just a second.
Okay.
The primary non-negotiable role of this entire system is maintaining homeostasis.
Keeping everything in balance.
Exactly. It's that constant effort to keep the body's internal environment stable, within those really narrow optimum parameters, no matter what's happening on the outside. Hormones are just the chemical messengers that make it all happen.
And the body's architecture for managing this is, it's just brilliant. It allows for a huge whole body impact from what starts as a really subtle signal.
It really is.
We're talking about that classic three-tiered regulatory hierarchy, right? The hypothalamus, the pituitary gland, and then the peripheral endocrine tissues.
And it's all about amplification. You have to think of it like a chemical cascade. It's designed for pure efficiency.
Okay, so walk me through that.
So a tiny neural signal hits the hypothalamus. It releases a very small amount of releasing hormone. That tiny signal then hits the pituitary, which amplifies it, releasing a much greater amount of stimulating hormone.
And then that hits the target gland.
That's the final stage. The peripheral gland gets that signal and just unleashes a massive surge of its target hormone, say cortisol or thyroxine, into the whole body. That signal gets amplified 3 times, so a whisper in the brain becomes a roar across the body.
That is a powerful engineering strategy. Okay, so we have the organizational chart. Now let's pivot to the messages themselves, the actual chemical signals and how they talk to the cells.
And this is truly fascinating and a critical distinction for any medical exam you'll take. A hormone's chemical structure dictates its entire mechanism of action.
How it's built determines how it works.
Precisely. And we can basically categorize them based on how they interact with the cell membrane. It splits them into 2 very different communication systems.
Let's start with the fast ones, the immediate responders. So the cell membrane is made of fat, right? How do these big water-soluble hormones get past that barrier?
Well, the short answer is they don't. The water-soluble hormones, and this includes things like polypeptides and modified amino acids like your catecholamines, they can't cross the membrane.
They're impermeable.
Exactly. So they have to rely on cell surface receptors, things like G-protein coupled or tyrosine kinase receptors. The hormone binds on the outside, and the signal gets relayed inside the cell. We call that signal transduction.
And that internal relay, that often involves the famous second messengers like cyclic AMP.
That's the one. And this mechanism has one huge clinical advantage: speed. It's incredibly fast because it doesn't need the cell to build anything new. It just activates or inhibits enzymes that are already there.
Like flipping a switch.
You got it. Think about the near instantaneous effect of adrenaline in a fight-or-flight response. That's what we're talking about. And it's worth remembering, polypeptides are the most common type of hormone. A safe bet on an exam.
So if the water-soluble hormones are like sending an instant text message, what's the analogy for the other side, the lipid-soluble ones?
That's an excellent analogy. If the fast ones are a text, then the lipid-soluble hormones, we're talking mainly about steroids, all derived from cholesterol, they're more like receiving a legal document.
Ah, okay. Slower, more impactful.
Exactly. Because they're fat-soluble, they just slide right across the cell membrane, no problem. Inside, they find intracellular receptors, either in the cytoplasm or the nucleus. And when they bind, they act directly as a transcription factor.
So they're not just flipping a switch on an enzyme, they're actually starting a long, slow process of genetic change.
Yes. They are stimulating or inhibiting the transcription of specific genes. That leads to making new proteins. It's a fundamentally different process. It takes way longer hours to days. But the change is much more profound and lasts a lot longer.
And it's not all top-down, is it? A target cell itself has some say in how much it listens to the hormone, regardless of how much is floating around.
It does, and that's all managed through receptor dynamics. If hormone levels are always low, the cell might try to become more sensitive by putting more receptors on its surface. We call that upregulation.
And the opposite.
If the system is just flooded with a hormone all the time, the cell protects itself from being overstimulated by reducing its number of receptors. And that's a downregulation.
It seems like a system that could easily spiral out of control. So what are the brakes? What keeps everything in check?
That comes down to the control loops. And the primary mechanism, the one that keeps us stable, is negative feedback.
The classic homeostatic loop.
Right. The hormone's own action reduces the intensity of the stimulus that started it all. A perfect example is high circulating thyroxine levels telling the hypothalamus and pituitary to, back off and release less TSH.
But because biology is never that simple, there's the rare exception, the non-homeostatic loop.
And that's positive feedback. This is where the hormone's effect actually promotes the stimulus that caused its release. The textbook example is the oxytocin loop in childbirth.
More oxytocin, stronger contractions, which causes more oxytocin release.
And it just keeps escalating until the stimulus the baby is removed. It's designed to push the system away from equilibrium to achieve a specific one-time event.
Okay, here's where it gets really interesting. Let's dive into the command center. The hypothalamic pituitary axis, or HPA. So anatomically, the hypothalamus is at the base of the forebrain, and the pituitary gland just kind of hangs down below it. But what's so special about their connection is the plumbing, that portal circulation.
That portal circulation is absolutely key, specifically for connecting the hypothalamus to the anterior pituitary. It's like a VIP highway.
How so?
It ensures that the tiny amounts of hormones from the hypothalamus get to their target cells in the anterior pituitary before they're just diluted into the general circulation. It allows for incredibly close, efficient regulation.
And that's a sharp contrast to the connection with the posterior pituitary, which isn't really a true gland at all, is it?
Not in the same way. It's more of a neurostorage and release depot. Axons that start way up in the hypothalamus stretch all the way down into the posterior pituitary.
And that's where they release ADH and oxytocin.
Directly into the bloodstream. So the hormones are made in the brain, but they're released from the pituitary.
Okay, back to the anterior lobe. Students always have mnemonics for the 6 cell types and their hormones. Somatotrophs for GH, gonadotrophs for LH and FSH, and so on. But these cell groups are really prone to tumors.
They are. And clinically, we spend a lot of time on pituitary adenomas. And of the ones that actually function and secrete hormones, prolactinomes are, by far, the most common.
And the way they present is a really high-yield clinical contrast, especially between men and women.
Absolutely. Because prolactin messes with the reproductive axis, women tend to present early. They'll have irregular periods or no periods at all, maybe infertility. Men, on the other hand, they might ignore reduced libido.
So they present later.
Much later, often.
Yeah.
And by then, the tumor's grown so large that they present not with hormonal issues, but with mass effect. Things like vision problems or severe headaches, that's what finally brings them in.
And if the pituitary gets damaged, say from compression or an infarction, we get the opposite problem, hypopituitarism.
Right, and panhypopituitarism is the deficiency of all the anterior hormones. Now, for diagnostic purposes, you have to remember the characteristic order of hormone loss. It's a very specific sequence.
Okay, what's the pattern?
Growth hormone is almost always lost first, then LH and FSH, then TSH, then ACTH. Prolactin is often last. It's a predictable cascade.
Which brings us to the posterior pituitary disorders, which are all about fluid balance. The most famous one being diabetes insipidus, or DI.
DI is all about the inability to conserve water. Either you're not making enough ADH, that's cranial DI, or your kidneys just aren't listening to it. That's nephrogenic DI.
And the result is polyuria and polydipsia.
Massive amounts of very dilute urine, which leads to intense thirst. It's a major dehydration risk.
So what's the opposite condition where you're holding on to too much water?
That would be the syndrome of inappropriate ADH secretion, or SIADH. Here you have way too much ADH, causing massive water retention. It dilutes your serum sodium.
Leading to hyponatremia.
A hypoosmotic hyponatremia. And the key clinical difference is this. In DI, you need to replace free water. In SIADH, you must restrict water.
Let's move down the axis to the peripheral glands, starting with the body's metabolic engine, the thyroid.
The thyroid's job is to regulate our baseline metabolism, our energy burn, but it's also absolutely crucial for CNS and skeletal development. And a unique high-yield fact about the thyroid
What's that?
is its storage capacity. It stores about 100 days worth of T3 and T4 in its follicles, which means a clinical deficiency can take a really long time to show up.
But when that metabolic rate goes into overdrive, we get hyperthyroidism or thyrotoxicosis.
And the classic presentation is pretty dramatic. Weight loss, but with an increased appetite, heat intolerance, a racing heart, a fine tremor.
And the most common cause is Graves' disease.
It is. That's an autoimmune condition. And when you're looking for Graves, you look for the specific signs. The exophthalmos, which is the bulging eyes, the lid lag, and that weird patchy thickened skin over the shins called pretibial myxoedema. And you always have to be aware of a thyroid storm, which is a life-threatening emergency.
On the flip side, an underactive thyroid, hypothyroidism, is especially dangerous in children.
This is a critical public health concept. Thyroid hormones are indispensable for normal brain development. A deficiency in newborn causes cretinism, which is irreversible mental retardation. That's why TSH screening is mandatory for all newborns.
Next up, the adrenal glands are stress managers. We have the outer cortex making steroids and the inner medulla pumping out catecholamines.
And focusing on the cortex, you have three zones making three groups of steroids. The outer zona glomerulosa makes aldosterone for fluid and electrolyte balance. The middle and largest zona fasciculata makes cortisol, our main stress hormone. And the inner zona reticularis makes androgens.
The key to understanding cortisol is that it's fundamentally catabolic, right? It's designed to break things down for survival.
Exactly. Its job is to prioritize the brain's energy supply. It fires up gluconeogenesis, it breaks down fat. But that's also why chronic excess is so damaging. It cannibalizes resources, breaks down muscle, strips calcium from bones, leading to osteoporosis. It's a powerful survival hormone that's not meant to be high all the time.
And when that system goes wrong, the clinical signs are unforgettable. Too much cortisol gives you Cushing's syndrome.
And the signs of Cushing's are all about that chronic excess. You get the fat redistribution, the famous moon face, the buffalo hump in the back of the neck, those wide purple abdominal striae.
And the opposite, a primary deficiency of both cortisol and aldosterone, is Addison's disease.
Primary adrenal insufficiency. These patients are severely fatigued, they have low blood pressure, and critical electrolyte problems, low sodium, high potassium, from the lack of aldosterone. But the most distinctive sign is the generalized skin pigmentation.
And that pigmentation is a huge high-yield question because it seems so counterintuitive. The adrenal cortex is failing, but the skin gets darker.
It does, and the answer goes right back to that negative feedback loop. When the adrenal cortex fails, cortisol levels plummet, so the pituitary is freed from negative feedback. It panics and starts screaming for cortisol by pumping out massive, unregulated amounts of ACTH.
And that's the key molecule.
It is, because the precursor molecule for ACTH is also the precursor for melanocyte-stimulating hormone, or MSH. So huge levels of ACTH basically act like MSH, stimulating pigment production in the skin.
Fascinating stuff. Okay, now let's shift to the organ that mostly stands apart from the HPA axis, the pancreas, our local glucose autoregulator.
And that independence is vital. The endocrine pancreas, the islets of Langerhans, is controlled directly by blood glucose levels, not by the hypothalamus. It needs to be immediately responsive.
And that response involves those two opposing hormones, insulin and glucagon.
Insulin, from the beta cells, is anabolic. It lowers blood glucose by helping cells take it up and store it. Glucagon, from the alpha cells, is catabolic. It raises blood glucose by telling the liver to release its stores. It's a perfect push-pull system.
Which brings us to the most common endocrine disorder on the planet, diabetes mellitus. Type 1 being insulin deficiency, type 2 being insulin resistance.
And the crucial clinical contrast between them is the risk of diabetic ketoacidosis, or DKA. This is a life-threatening emergency that really only happens when there's a complete or near-complete absence of insulin.
Which is typically in type 1.
Right. With no insulin, glucose can't get into the cells.
Mm-hmm.
The body thinks it's starving and starts breaking down fat for energy. That process produces acidic ketone bodies, leading to a profound metabolic acidosis. That total lack of insulin is the absolute key.
And beyond glucose, the system also manages other huge homeostatic tasks like fluid balance with ADH and the renin-angiotensin-aldosterone system, the RAS.
And just remember, aldosterone from the adrenal cortex is a core part of that RAS system. It saves sodium and water to keep your blood volume up.
And finally, that incredibly tight control over calcium homeostasis, which is mostly run by parathyroid hormone, or PTH.
PTH's job is simple. Raise serum calcium if it drops. It does that by pulling it from bone, saving it in the kidney, and, crucially, activating vitamin D to absorb more from the gut.
And if you have too much calcium, you have to remember that classic mnemonic.
Bones, stones, abdominal groans, and psychic moans. It covers everything. Bone pain, kidney stones, constipation, and confusion or mood changes.
We can't finish a deep dive without looking at the future, especially the growing importance of these GI tract peptides.
Oh, this is a huge area. These are peptides from neuroendocrine cells in the gut that link what you eat directly to your metabolism. GLP-1 is the big one right now.
Why is this so important?
It enhances insulin release, and it promotes satiety. It makes you feel full. It's a powerful weight regulator, which is exactly why GLP-1 agonists and DPP-4 inhibitors, which stop GLP-1 from being broken down, are now cornerstone treatments for type 2 diabetes. So what does this all mean? We've covered a ton, from the two basic hormone mechanisms, the fast surface receptors versus the slow gene-altering ones, all the way to the major diseases. The key takeaway, especially for you learners, is that endocrinology is all about understanding control, the interdependence of the hypothalamus, the pituitary, and the target glands. That is the path to real clinical insight.
That was a tremendous synthesis. And to reinforce one of the most high-yield points we covered, let's leave you all with a short review exercise.
Imagine a patient comes into the emergency department. They have severe fatigue, their blood pressure is dangerously low, and they have this generalized hyperpigmentation across their palms and gums. Which adrenal condition is strongly suspected, and why do they have that skin darkening despite a profound deficiency of adrenal hormones?
Think about that unique high-yield connection we talked about involving ACTH and MSH. Mull that over, and we'll catch you on the next deep dive.